Hi everyone, my name is Jackson Ponsler and this is another 5-minute lesson. Today I'm going to be talking about rotational matrices. This was taught in my Introduction to Robotics class by Dr. Hollerbach. Just giving credit to him. This is just going to be a brief summary of what rotational matrices are and how you can build them and what they do. If we were to have an axis or a coordinate system here, like if I had X and if I had Y, and I wanted to change them into this second pair, X2 and Y2, what I can essentially do is by just rotating the axes by some theta, I can achieve this goal. I can change it, I can translate them into this new state. To do this with any vector or axes, you apply what's known as a rotational matrix. So just as this was a rotation of theta, I put down here R of theta. And Dr. Hollerbach's notation is I'm going from the first to the second. So R2R1 of theta is going to actually be the cosine theta of that angle, sine theta of the angle, negative sine of the angle, and cosine of that theta. And by timesing this by, let's say, x1, I can change it. So let's call this, let's label this right now. x1 will be 1, 0. We'll have the theta be pi fourths. And so that means that our rotational axes will be square root 2 over 2, square root 2 over 2, negative square root 2 over 2, square root 2 over 2. And so when I do x1 times this rotation, I should get x1 written in terms of 2. I wrote this notation wrong. It's supposed to be R21 of pi fourths times x1 of 1. You want to make sure that the ones line up because it's going to change it. And then you just do it straight across. So I take my x1, I take this, plug it into my x1. So that means I've got square root 2 over 2, and when you do it again to this bottom, so take this bottom row times it there, that gives me square root 2 over 2. And that's the basics of how it works. By having this rotational matrix, you can take any vector and a coordinate system, which is a group of vectors, and transform into another axis. The other unique thing about rotational matrices is if you want to do the inverse, so let's say R1 to 2 of theta, it actually equals R of theta 1, 2 transpose. And the reason why this works is because if I want to take this angle, if I want to do the reverse, do x2 to x1, I'm moving by this negative theta. And so because I'm moving by that negative theta, it's essentially the same as just swapping these around, which is just transposed. So if you're trying to move from one system to another system, and you already know it going to one system, then you just use the transposed version, sorry about that, it's transposed version of the rotational matrix to get back to there. Final step is, if I was to then, let's say, rotate a final few degrees to make it 180 degrees, so this would be x3, y3, I can get to there by taking my x1, and then I can take R3, so I'm going from 2 to 3, and I'm going to times it by my rotation matrices going from 1 to 2, so put x1, and that will allow me to get it to this third one, which would be x on the third coordinate system. So basically, by timesing multiple rotational matrices together in the proper order, you can create a matrix that already encompasses the other rotational matrices. And that's all the time I have today. My name is Jackson Ponsler. Thank you so much for watching, everyone. Hope you look forward to the next one.